All right, let's just dive right in. I want you to forget everything you thought you knew about algebra being some boring chore. Seriously, today we're not doing math homework. We're detectives, and we've got a mystery on our hands. Our mission? To track down and unmask the true identity of the most elusive character in mathematics, the variable x. Just think about that for a second. What if every equation was a crime scene, just filled with clues, suspects, and a fundamental logic that's just waiting for you to crack it? Well, by the end of this, you are going to have the complete detective's toolkit to solve for x every single time. So first things first, let's open the case file. We're looking at linear equations. Think of them as these perfectly balanced statements. Our main suspect, x, is hiding its value, and our whole job is to isolate it, to get it all by itself so we can finally discover its true identity. Now listen up, because every good investigation has one golden rule, one law you can never, ever break. For us, it's the law of balance. That equal sign, that's the center of our scale. To keep our investigation totally fair and our clues valid, any action we take on one side, any operation, any move, we have to do the exact same thing to the other side. This one is non-negotiable. Okay, so to really get a handle on this whole balance thing, we need to visualize the evidence. So we're going to use this cool tool called algebra tiles. They let us turn an abstract equation into something physical, something we can actually touch and move around. It makes the idea of balance perfectly clear. So here's our visual language, our key to the code. A clear rectangle, that's a positive x. The shaded one is a negative x. The little clear square is a +1, and the shaded one is a -1. Simple, right? These are all the pieces of our puzzle. And right here, you can see exactly how those two worlds connect. On the left, we've got the physical evidence, 3 of our x tiles and 2 positive units, balanced against 11 positive units. And on the right, you see the symbolic equation from the case file, 3x + 2 = 11. It's the exact same story, just told in 2 different languages. So how do we actually solve this with the tiles? Well, first, we simplify the scene. We take away 2 units from the left, and to keep that balance, we have to take away 2 from the right. Now we're left with 3 x's on one side and 9 units on the other. To find the value of a single x, we just divide those 9 units into 3 equal groups. And just like that, the solution becomes crystal clear. Each x lines up perfectly with 3 units. Case solved. X = 3. Tiles are fantastic for getting the concept down. I mean, they're great. But a master detective needs faster tools. So now we're going to graduate from the physical tiles to the real power and efficiency of symbolic algebra. Okay, so here's the crucial idea. Every single mathematical operation has an opposite, basically an undo button. We call these inverse operations. Addition and subtraction, they cancel each other out. And it's the same for multiplication and division. These are the tools we're going to use to systematically dismantle the equation and isolate x. So to figure out which tool to grab, we look right at our suspect, x, and we ask this one simple question. What's happening to you? Is it being multiplied by something? Is there something being added to it? Once we identify what's being done to x, we know exactly which inverse operations to use to set it free. Now, here is a secret that trips up so many people. You probably learned the order of operations for doing math, BEDMAS. Brackets, exponents, division, multiplication, addition, subtraction. Well, to solve an equation, to undo it, you have to work backwards. We use reverse BEDMAS. That means we deal with addition or subtraction first, and then we handle the multiplication or division. We are literally rewinding the tape of what happened to x. All right, with our basic toolkit ready to go, let's start tackling some tougher mysteries. Yeah, the cases might look more complex on the surface, but the core principles we've just learned, they're all we need to crack them. So sometimes the evidence is just scattered all over the place. Here, we've got a couple of x terms just hanging out on the same side of the equation. So our first step is to clean up the scene by combining like terms. Think of it like grouping all your x suspects together. So 5x minus 2x just becomes 3x. And all of a sudden, a messy-looking equation turns into a simple 2-step case that we already know exactly how to solve.
So what happens when our suspect x shows up on both sides of the equal sign? No big deal, we just go back to our golden rule, the law of balance. We pick one of the x terms, usually the smaller one, just to avoid negative numbers, so the 4x here, and we get rid of it using its inverse. By subtracting 4x from both sides, we get all our suspects onto one side of the equation, turning another complex case into a really straightforward one.
Ah, the locked room mystery. Sometimes our clues are trapped inside brackets, parentheses. To get them out, we need a special key, and that key is called the distributive property. Now, the rule here is simple, but it is absolutely critical. The number outside the brackets has to be multiplied by every single term inside. Not just the first one, all of them. So in this case, the 7 multiplies the x, and it multiplies the 2. And boom, just like that. By distributing that 7, the brackets are unlocked and they disappear. Our case file now reads 7x plus 14 equals 3x minus 6. And look at that. We've turned a locked room mystery into a standard variables on both sides case, which we already totally know how to solve. Okay, we think we found our culprit. We've isolated x, we have a value, but a great detective never closes a case without being 100% sure. This final step is crucial. You have to verify the solution. Let me show you why this is so important. Let's say we were solving an equation and we made a little mistake and we thought x was equal to -2. Well, when we plug that value back in to check our work, the left side becomes 11, but the right side is -3. 11 does not equal -3. The scales are completely out of balance. Our check just proved without a doubt that we have the wrong suspect. But when we go back and do the work correctly for that same equation, we find the real culprit is x equals 5. So let's plug that back into the original equation. The left side becomes -3, and the right side is also -3. The balance is perfect. The evidence is conclusive. Now the case is closed.
So there you have it. That is your complete detective's toolkit. Always remember the law of balance. Use your inverse operations in that reverse speed mass order, tidy up messy cases by combining and distributing, and always, always check your work.
See, math is no longer just a set of rules to memorize. It's a series of puzzles just waiting for you to solve them. You are now officially a code cracker, an equation detective. So the only question left is, with this new toolkit in your hands, what mystery are you going to solve next?